Hey guys, welcome back to the vlog. In today's video I want to talk about the Central Limit Theorem, okay, in dealing with two populations. So in some of these examples we may be given more than one group, and in doing so we can then compare them using the Central Limit Theorem, and we will walk through two examples of how to do that. Some points to think about is we have a mean that we're going to be given, okay, so we'll be given a mean, we'll be given a standard deviation, and we'll be given the number of observations for both groups. Once we know that we have this information here, we can then use the following formula, transforming it to, of course, the z value. So the formula is going to be z equals x1 minus x2 bar, so we're going to have our sample means, and then we're going to subtract the difference between our population means, and then we're going to divide by our standard deviation of number 1 over the square root of n of 1 minus standard deviation of 2 over the square root of n2. So it looks very similar to the Central Limit Theorem formula, except we're going to be adding our population means here, and then we're going to be looking at the difference between our bottom values, which is the standard deviation over the square root of n. So this is the formula that you use when looking at two populations using the Central Limit Theorem. So let's go ahead and look at two examples of using this. Okay, so for our first example we are given this question. Find the probability that our gecko will outlive our chameleon by 3.5 years given the following information. So down here on the left hand side we know that on average a population of geckos has a lifespan of 15.6 years, has a standard deviation of 4.2, and we've measured 62 geckos. The chameleons, on the other hand, have an average population lifespan of 13.1 years. We have a standard deviation of 2.2, and we measured 50 chameleons to get these metrics. So now that we have that, let's go ahead and write down our z formula. So we know that z is equal to x bar 1 minus x bar 2 minus our population means. So we're going to have 15.6 minus 13.1, and then we divide by 4.2 over the square root of 62 minus 2.2 over the square root of 50. So that's how we start off writing things down that we are given in the question. Now this x bar 1 minus x bar 2, you may be wondering how we figure out what that is. Well, it's actually given to us in the question. We want to find the probability that there is a difference of at least 3.5 years between the gecko and the chameleon. So the same formula would apply. So we're going to have 3.5 here minus 2.5. We're going to divide that by 0.222. So that's how we use the Central Limit Theorem with two populations using the formula given. And the tricky part is figuring out the x bar 1 minus x bar 2. Most of the time it's going to be hidden within your question because it's what we're going to be looking at as far as a difference. So in this case, the probability that our gecko will outlive our chameleon by 3.5 years. So that would be the difference here. So once we do that, this gives us a z value of 4.50. So the question is asking the probability that z is greater than or equal to 4.50. So in order to do that, we need to go to our standard normal table on the positive side and figure out what that probability is. So let's go ahead and jump over to that. Okay, so here we have the positive side of the standard normal table. And our value was 4.50, so we would go ahead and search for 4.50? Well, of course, it's off the chart, which means this probability here is from this way over. So if we want to figure out what this way is, or the probability greater than that, we simply take 1 minus the probability within the table. So we'll just go ahead and we'll go back and we'll do 1 minus 0.9990. So to do this, we will just simply take 1 minus 0.9990, which of course we know that the probability is going to be less than 0.0010. So there's a 0.10% chance that our gecko will outlive our chameleon by 3.5 years. So they're going to be within 3.5 years of one another. So that's our first example, comparing two populations using the central limit theorem, converting it over to the z-score, and then using our standard normal table to find the probability of what we're asking. So let's look at our second example. For this example, we want to find the probability that tiger sharks will have a length that is at most 44.2 inches more than hammerhead sharks, given this information. So over on the left-hand side here, we have the lengths of our tiger sharks from a population perspective. We have 72 inches as an average, 10 as our standard deviation, and 64 as our total population number that was observed. Hammerhead sharks, average length 28 inches, standard deviation of 5 inches, and our n value equals 100. So let's use our z formula to calculate this probability. So we're going to have z equals x1 bar minus x2 bar, and then we're given the populations. So it's going to be minus 72 minus 28, and we're going to divide by the difference between 10 over the square root of 64 minus 5 over the square root of 100. Again, in this example, it's at most 44.2 inches, so that 44.2 inches is what fits into our x1 minus x2 spot, because that is what we are looking to get a z-score of, the probability of this. So again, if we fill these in, our z is going to be equal to 44.2 minus 44, and we're going to divide by 1.346, and that gives us a z value of approximately 0.15. So now that we know our z value, the question is asking, find the probability that tiger sharks will have a length that is at most. So what that means is the probability that our z is less than or equal to 0.15, right? Because at most, so we can't go over that, and since we converted it to a z-score, it has to be less than this or up to it. So the probability of 0.15. So let's jump over to our standard normal table to find the probability of 0.15. Alright, so here we are at the positive side again of the standard normal table, and our value is equal to 0.15. So this number right here. So it's 0.5596. So the probability that a tiger shark will have a length that is at most 44.2 inches more than hammerhead sharks is 0.5596. Or we can write this as 55.96% chance that tiger sharks will have a length that is at most 44.2 inches more. So that's a second example using the central limit theorem when comparing against two different populations. So there you have it, two quick examples of walking through the central limit theorem and comparing two populations against one another. As always, guys, I thank you for watching the videos. If you have any comments or questions, feel free to comment down below. Like and subscribe, and we'll see you in the next video.